Okay, thank you. I'm sorry for the delay. I tried before lunch. Everything worked fine. Okay, I am this work I have done with Franco Di Rino and Marcelo Stacchiotti. They are my colleagues in Argentina. We are from Rosario. Rosario is about 5,000 kilometers south from Natal, and there's winter. They are 8 degrees now. Probably you know Rosario because it's the born city from Messi, one of the best known soccer players. Okay, we are doing some theoretical working with this kind of atomistic model. So we are dealing with in the multi-scale, in the scale length of as Jorge Ñíguez in this second principle model. This is a classical model, just where the system is described by atoms, and atoms, in order to describe ferroelectric properties, the atoms have to be described with a shell that somehow take into account the electronic contribution to the polarization. So in general, our model descriptions can be decomposed in different interactions between atoms. We have the classic core and shell, the coupling between the core and the shell on the same atom, Coulombic interactions, and short-range interactions of different types. This is the idea. They are all pairs, yes. No, sometimes we consider some three-body interaction, but not very much. So we did some previous work before. Okay. This is a few years ago we started to study this. Okay, we have this model. We fit it. We adjust the parameters to describe the bulk. But when we try to study surfaces, it worked very fine. So we go to study nanoparticles, and it also worked pretty well. So this is some resume of the result we have previously. I see. Okay, this is also if we make these nanoparticles with rectangular shapes, so we observe that. Okay, here they're elongated. They form the vortex state along one direction. Now, if we make cubes, now the vortex core is along one direction, no? Along the diagonal of the cubic cell. So here are some pattern of the polarizations. So, and we try to understand what happens if we change the aspect ratio. No, we say we keep fix the height and expand the lateral size. So first we observe a transition to a structure with 4 vortexes. No? They are perpendicular to the surfaces, and here they, as a result, they made these 4 domains, 2 pointing up in red and 2 pointing down. No? Okay, we start to increase the lateral size, and we observe this ferroelectric bubble. No? We think this was made because the vortex, now they are aligned along the closed path, and inside we observe this ferroelectric bubble. Is increasing even more, we start this bubble transforms, they start to elongate and transform into the strip domains. So in the limit, the system becomes a thin film. So somehow we went from a small particle to a 2D system. The thing is, we have to stop to this simulation and then say, okay, what's happened is we try to analyze different shapes. No? How this behavior is affected by the shape or the size of the particle. So, okay, let's go with cylinders. So, okay, how we make cylinders, because we try to, our unit cell, this is the small particle we have, and we try to build some a circle. So our circles are not real circles. No? So we are playing like a Lego toy, so to build our system. So this is, as the system become bigger, these differences are less appreciable. So this is something like the framework that over there we put our atoms. Bien, how we made the simulation? In general, we perform molecular dynamic simulation with our model, so we keep in constant the number of particles and the temperature. No? So we work with isolated particles, like freestanding particles, surrounded by vacuum, no periodic boundary conditions, nothing. So the initial configurations, so we put in the ideal perovskite position the atoms, and from this point, we start to relax without any restrictions. No? So we made our simulations. In general, we start at 0 temperature, but warm up the systems and change time to time in order to avoid different metastable state, even though we cannot be sure if they are the configuration we are showing are the real ground state. No? Okay, how we calculate the properties? We define the polarization in each unit cell, and also we estimate the toroidal moment of the particles. So the first thing is that, okay, we have cylinders with the same diameter and height. I said, what happened? This is what we observe in the case of D equal 11. So they are cut in planes showing the polarizations pointing perpendicular to the plane of the cut that go through the center of the cylinder. So if we observe the polarization, the X components, so we have two domains. The same is we made a perpendicular cut. It's the same behavior for the Y component of the polarization. So the thing is, if we made a cut at the center with an XY plane, we observe here also we have the vortex configuration of the local polarization. So this means that the polarization are rotated along 001 direction, and it has a really quite homogeneous behavior all along the cylinder. Okay, we did this for different diameters, no? Increasing the size, and we observe that the toroidal moment remains along the Z direction and is growing with the size of the cylinder. And in addition, in the inside, we are showing the polarization that is also growing the size with the size. So this is the main reason of the increment of the toroidal moment. I say, okay, but what happened is we looked the polarization profiles, no? Like we did this for 11. So, okay, this is for D equal 15, and we observe, okay, the vortex, we see the central vortex rotated, no? But the polarization start to align each other, no? Trying to forming a domain, regions with similar polarization. If we increase a little more, so now the polarization are getting bigger. The central core seems to distort. The domains are more defined, even though the localization of the domain walls are really hard to figure it out. Here it looks one are in the 100 direction and perpendicular. It increases even more. The central core start to distort as the domains start to be better defined. No, this is the same. So we see the bigger distortion. We also start to know that okay, domains become different. No, you have two different domains. The left and the right domain are bigger from the top and bottom domains. No, and this is the biggest we perform. Say, okay, that's look really strange. We try to get more detailed information. I mean, the thing is, the behavior of these cylinders in the phenomenological description are described in terms of dipolar energy, elastic energy and energy related to the surfaces. So the energy for us came with the contribution of atoms, so it was no straightforward to discriminate this contribution. Say, okay, what can we do? Okay, we try to plot, let's say, the polarization, just the polarization and the magnitude of the polarization. Somehow, probably we can take some information. So, sorry, this is how the core is evolved. No? Here is like have more circular shape, start to distort and elongate, and they are elongated even more with the time. This is similar to what was predicted by Ruiz and Scott, that they say that, okay, this fourfold domain wall junction is going to be unstable and will break into this different kind of domain. It's not the same, but we are looking something similar. So this is what I was talking. No? Here we can observe in a more clear way the 5 domain walls we have. We have the 2 up and 2 down are 90-degree domain walls, and there is 180 degrees domain. No? Even though it's not parallel to the polar direction of the domains. What else we can observe here? First, there is a strip along the domain wall where the polarization gets bigger. No? What else? Here, the biggest polarization we have at the 100-degree domain walls, and we have also in these places, another place where the polarizations is not along one, that is something like other domains. No? The polarization is pointing 110 direction. No? They are bigger. And in general, okay, and over the surfaces, the polarization is lower, and it looks like that this continuous curling of the polarization. So we can get very much info, at least qualitative description from this kind of picture. Okay, now you say, what happened is we start to elongate the cylinders. The thing is, we did it for this case for DUL25, and we observed that the behavior remains similar. So the behavior is independent of the height of the cylinder. We saw the same kind of structure as we saw with the different diameters, that these vortex structures are really similar, but just depend on the height of the cylinders. No? In addition, we don't observe any vortex structure with core perpendicular to the z-axis. So now, okay, what happens is we start to increase the aspect ratio. No? We had fixed the height and start to increase the diameter. Here also we observe the same behavior that we observe in rectangular particles, so the presence of 4 domains, 2 pointing up and 2 pointing down. If we perform a cut in x plane, here we can observe 2 vortices rotating in opposite directions, and we another in the perpendicular plane, we observing also other 2 vortices rotating in different directions. So in that way, the path is not, even though it's not closed yet, because the directions are not continuous, the change of the directions. So this is pretty much the same. So we start to increase, we start to observe again the we call ferroelectric bubble after the Ramesh said, we can talk about skyrmion. So we have this now. So this is a similar cutting place. One can observe that the vortex now are rotating. They make a closed loop, where the polarization making a torus, and we have a strong polarization inside pointing up and outside pointing down. Now, this is similar. This is just a picture of how is our ferroelectric bubble view in a 3D case. This is the core of the bubble. This is similar to what we observed in the rectangular nanoparticles, also with the same aspect ratio. Now, if we're still increasing, we go from one bubble to two bubble state. Now the bubbles are not elongated because of the symmetry confinement. And again, if we still increase more the system, we have to 5 bubbles with this periodic domain structure. And this is for the largest nanodisk we have. And the behavior also is getting close to the thin field. So in the limit, we reach the thin field behavior. In general, we observe that the width of domain just depends on the height. It doesn't. And it remains almost constant as the system increases. The new stripes or domains or bubbles, are emerge as they have some space. But in general, the width remains nearly constant, and it depends just on the height of the cylinder. That follows as it's constant. Okay, what happens if we have some spheres? Okay, the system, the polarization also here. Our sphere have 3 equivalent axes, around the Cartesian direction. And depending on the situation, the board we have observed only one chord that can go to any one of these 3, and we have a similar behavior that's in the cylinders, but only just one chord along the center of the sphere. So we do for different diameters, and we observe always the same result. Now we try to deform these spheroids. We make some elongated or prolate spheroids. Again, we can see this spheroid as intermediate shape between a large cylinder and a sphere in the limit. So we observe nearly the similar type of behavior. So just one core pointed along the longest direction. So now, this is other case. This is that we are just new result. We are not clear. This is the longest spheroid. It had 51 celos length. We can see that in our simulation, they change the chirality of the two regions with that change the circulation. At some point, one point is circulating in one way. At the half, they change. It's pretty stable, this configuration. I don't know if it's the most stable. We try to get one with just one vortex in one direction of circulation, but we couldn't get it yet. So, but the thing is, this configuration with two directions, opposite directions, the rotation direction are pretty stable. Okay, and finally, we say these oblate spheroids. The first things transformation we observe as when they become flat. Now the vortex try to like one of these longest directions, and start to split. No? So this is the difference we perform is at the start we try to say, okay, we are seeing the same path we observe with the disk, but however, we couldn't get the ferroelectric bubble. So this intermediate state doesn't show up. So we think it's something related to the effective surfaces we have. No? We have like something flat surfaces that are thicker at the center and start to become thinner when you go out close to the surfaces. So somehow these configurations do not allow to stabilize the ferroelectric bubble, even though we can go directly to the stripes domains. Okay, this is what we are performing right now. This is all my new results that I have. This is something for the summary. So we have explored the structures. We continue. Actually, we confirm that, no? We're supporting that the idea that is the smallest order structure in nanoparticles. Okay, these are all the summary, and that's all. Thank you very much.